Okay, so there we go. Recording's going. Okay, so let's see here. So again, thank you, Fernando, for the discussion of Section 3.4. A couple of logistical observations I'm going to make. So we didn't have the capability of recording Fernando's talk there, but if you'd like to be able to hear discussion on that same subject, I'm going to be talking about that material in my other sections of Math 219, and of course I upload all of those recordings up onto the same YouTube channel as this one. So you'll have it'll be a different point of view, but anyway, you can have a video reference to that stuff. And also, Fernando, would you mind sharing your lecture notes?
Yeah.
Okay, thank you, because there were some really excellent examples there. And do you mind if I share them with the class?
Yeah.
Just send them email to me, and I'll post them. Thank you. Okay. The other thing, and I just wanted to emphasize. So, 3.4 is a weird section in the book. It is arguably pretty premature. We're going to revisit all of that stuff when we get to chapter 7. Some of 6, but mostly 7. And so the idea, the reason Kali has that section, way early in chapter 3 is to kind of plant some seeds, get the ideas kind of mulling around in your head a little bit, and then all of the assertions that Fernando made in his presentation, we're going to solidify all of that to at least some degree when we get into chapter 6 and 7. I'll also point out, by the way, that even what we're going to do in this course, even what they do in Math 222, which is all about rigor and proof and stuff like that, it's still kind of tip of the iceberg. It's an extremely deep, heavy topic. There's no limit to the complexity and subtleties of that kind of stuff. What we're going to do in Math 219 will be very self-contained, though, and so anyway. All right, so here's where we were last time. We were talking about vector fields and flux, and I made this. Let's see. Let me go back to where we did a couple of observations. If your vector field represents velocity, then this thing called flux, this formula right here, was the answer to a very reasonable question, namely, how much water is coming out of my water hose? Right? What's the volume per unit time? How much total quantity of fluid in terms of volume per unit time? And then we also saw that if you throw in an extra factor of density on the vector field, then you don't get volume, you get mass per unit time, which I think is a pretty easy pitch, right? I mean, volume, density, mass, we already knew they were related. Okay. All right, so we had that. Seems like a nice, simple story, but then I introduced this complexity where we have two different light sources, each of which is making a different flow of photons, for example, which again are a kind of a fluid. And so at a given point, you look at a point like this, and you can't say what the velocity is at that point because there's photons going in two different directions at that point. So this kind of a fluid, where, imagine if you had a flock of birds, how they all kind of fly in some sense with each other, kind of together, right? Imagine they were just kind of they were just going every which way, right? They'd be colliding all the time, I'm sure. Conveniently, photons just pass right through each other and there's no issue there. But, so this kind of a fluid, though, how do we represent it with a vector field if we can't talk about the velocity? Well, the idea is that flux kind of comes to our aid here. So, we went through the details of this last time, but usually we think of that we have a vector field given to us describing the flow, and then we ask how much fluid per unit time is passing through a surface. And we're going to turn that around now and say, suppose we know already, empirically, how much fluid per unit time is flowing through any given surface. Can we reverse engineer what a vector field is that would give us that flow rate per this usual formula? Okay. All right. So I'm going to continue now with an example we were talking about of how to, how we can use this So recall we had this uniform ball of glowing gas, right? If you want to think of the sun as being a nice example of such a thing, then that's fine. But I don't know, I find that a little threatening. I don't know, it's very hot, you know. So I don't know, I'm kind of thinking like neon or something like that, right? So anyway, we argued last time that if you're interested in understanding the vector field, oh my gosh, right? The photons are going every which way. It's hard to describe. I mean, at any point, there's photons from here going that way, and photons from here going that way, and photons from here going that way. It's a nightmare, even at this one point, right? But flux is an easier thing to talk about, as it turns out. So in particular, let's think about flux through this sphere. How many photons per unit time are flowing out of there? Well, there's only two kinds of photons. There's the kinds of photons that originate from the inside. How many of them flow through this surface? All of them. Exactly once. Then there's the photons that originate from the outside, like over here. And those photons, the thing is, they do two things. They flow, color choices, they flow in through the surface, but then they also pretty much immediately just flow right back out through the surface. Every photon that flows in also flows out. In is negative flux, out is positive flux, and so grand total 0. Right? So if I'm interested in flux, I get to ignore all of the glowing gas on the outside of the sphere. Right? So this is a really powerful observation to make, and therefore it's only the gas on the inside, and therefore only the volume of gas on the inside because of the uniformity. It's only the volume of the gas on the inside that'll affect your flow. More volume, more gas, more photons, more flux. Is everybody with me? All right. Okay. Right. So with that settled, here's the calculation where we can find the vector field. Now, this is a delicate calculation. This calculation only works because of the really nice symmetries that we're assuming in this problem. This is a symmetric sphere. That's really important. It is a uniform sphere. The gas is uniformly distributed. That's a big deal. We really need that. Anyway, first observation I'm going to make, I feel like this vector field ought to be radial. I mean, everything else is symmetric. Wouldn't it be weird if somehow at a point like this, if the somehow the vector field describing the flow were that way, you'd be like, why that way? Why not this way? Why not that way? I mean, what is it about? How could there be an off radial direction? It's just everything's symmetric. It's not possible. Okay, so the vector field needs to be symmetric. Radially symmetric. Okay. All right. Next observation. Don't forget that our unit normal vectors are always perpendicular to the surface, and because I've chosen here a sphere centered at the origin, perpendicular to the surface is also radial. Right? So when I look at vector field, got our vector field F here, I got vector field dot unit normal vector. I'm dotting two vectors that are pointing in exactly the same direction. And so I'm just going to get the product of the magnitudes. Oh wait, one of them's a unit vector. I'm just going to get the magnitude then of the F vector field. Just magnitude of F. Everybody follow that part? Yeah.
So is K just a scalar?
Yeah, K is the way I wiggle out of issues I don't want to worry about, such as what do we mean by like how much energy is in a photon, and just how much is this gas glowing, and all these constants and units, and that's somebody else's problem I don't want to deal with. So yeah, so whatever, all of that stuff, I lump it all together in K. Is that reasonable? Yeah, cool. Good question. Okay, so with this observation made, we're pretty much in business. Let me remind you, we up here agreed that volume dictates flux. Right? Let me get ahead of myself here a little bit. I claim that equation is going to turn into this equation, and what I'm going to do is develop. Oh, sorry. Go ahead.
Yeah, no. So I was just asking, since we're taking the sphere here, and you just took the formula for the volume of the sphere, can we just use any 3D object?
No, the symmetries are really delicate on this, sadly. So, it's the argument that I'm making here is highly dependent on everything being symmetric.
So the cube is impossible.
It's not. It doesn't have enough symmetries, because I mean the point is the flux through kind of one of the corners or near one of the corners. Well, it's kind of an angle there, and it's not exactly, the normal is not perpendicular to the radial. It's just it doesn't work out nicely. Yeah. Okay, so this comes from the symmetries of the question. I claim that this equation is going to turn into this equation, and so that's just to let you know where we're going. And now how to get there, well, don't forget, first thing, that we have this formula here, defining vector field. What do we mean by a vector field representing whatever weirdo flow of photons this is? Well, I mean that dm dt needs to be computed with this formula for flux. The vector field has to fit this formula for flux. That's its job. So I need that to be true. Next, don't forget, we've already agreed that F dot n is just the magnitude of F. Here, right? And then also, don't forget that we have a standing formula for the area of a sphere, and that's 4 pi r squared. That's just old high school geometry fact. Oh, also, old high school geometry fact is the fact that volume is 4/3 pi r cubed. So, couple observations there, and nice punchline though. I've got an equation here from which I can infer the magnitude of my vector field. I still don't know the vector field itself, but I do know that the magnitude has to be, well, again, constants, not our problem, but proportional to r, proportional to distance from the origin. And then it's kind of all over, because I already knew furthermore that F should be radial, and in fact there is only one vector field that is both radial and whose magnitude follows this rule, and that is this formula right here. So there's our formula for the vector field describing this flow, and not at all obvious that it should be this, right? We had to do a bunch of work and make a bunch of arguments to get to it. But nevertheless, it does remain that if you find yourself looking at a situation like this and you want to compute a flux, this is the vector field that you do it with. So, not that the photons are doing this, right? Again, they're not. The photons are flying every which way. But in terms of net flux, this is the thing that will compute flux for you. Okay. All right. So next thing I want to talk about, this is just a definition that needs to get made. It's that of something called a flow line. It's a very natural concept. If you have a vector field representing the flow of a fluid, let's momentarily think of the fluid as being represented by way of its velocity. Right? Forget about density. This doesn't have anything to do with what we're doing here. And so, the vector field represents the velocity of the fluid. What would happen if you were to take a particle and drop it into the fluid? And I'm thinking of a lightweight particle that doesn't have inertia to speak of. And short version, I want to say it does exactly what the fluid tells it to do. If you drop a leaf on the surface of a river, it doesn't resist the river; it just goes along with the river. Yeah, it's all right. Everybody buy it? Okay. All right. So, all right. Well, then here's the claim. The English language claim that I've made here, I'm going to say the same exact thing now, but in math language, and that is that the velocity of the particle has to be the velocity of the fluid. Specifically, if you want to know what the velocity of the particle is when it's at a certain location, well, I need to know the velocity of the fluid at that location where the particle is. Right? Wherever the particle is, the fluid has got some velocity. The particle has to follow the fluid and therefore have exactly that same velocity. And then, of course, don't forget, velocity is what the vector field is that describes our fluid. So altogether, then, what we get is this equation right here. This is called a system of differential equations. Y'all don't have the tools yet to solve systems of differential equations. But you will when you get to Math 353. What we can do is we can confirm solutions to differential equations. And that's what this example here does. Here is a fluid flow right there. Right? And let's see here. That by the way, we've seen this vector field before. I hope you all recognize this one. This is the one where the fluid goes kind of counterclockwise around the origin. Right? It was one of our earlier examples. And so, what does the particle do if you were to drop it into this fluid? Well, the fluid's going around in circles. Wouldn't you speculate that the particle would go around in circles as well? And, well, here that is. There's a path. This is a parameterization of a path describing literally going around in a circle. And I claim that if you take this, if you compute its derivative to get the velocity of that particle, if you evaluate and see what is the fluid's velocity at that same point, what you will find is that you get the same thing. So, said differently, you can just directly confirm. It's just algebra. You just plug it right in, and sure enough, it works. And so this is this is what we call then a flow line. I should leave this in blue. This is called a flow line of that vector field. All right. Okay, so and that pretty much does it. We are out of time, and so we're now just done with Chapter 3, picking up with Chapter 5 on Wednesday. Good to see y'all. Have a good one. Oh, and don't forget to stick around if you came in after I did attendance. Stick around and make sure that